Okay, welcome to the video portion of this webinar. We're doing a video because I'm always a little nervous about doing live demos with software, although I think the risk is probably low, but we're going to do this anyway. And this is attempt number 2. My first attempt at a video, I got a little over enthusiastic about explaining everything, and it was a 25-minute video. So I don't think you want to sit through that. So we're going to get to the point a lot more quickly in this one. And what we want to show you then is quickly the process of getting to a model, and then how we would use that model. That's the main point, how we would use that model as a model-based management kind of tool. All right, so let's get going on it. This one is, what you're seeing here on the screen is the static line design calculation worksheet. So it's an Excel worksheet. And this is typically our starting point. So we would define the products we want to include in our design, in our design and also in our model, and how many. So that's our target volume or capacity for this design. We need to have work content information, like how long does it take to do the work, by model, by process, and the processes are listed across the top here. These columns, like spoke installation. By the way, this is a bicycle manufacturing factory that we use in our live workshops as well. And then we do some calculations. You're probably already familiar with this. So we calculate takt time, we calculate resources, and then we define how many workstations, how many machines, et cetera, to support that capacity goal within a certain amount of time. In this case, it's 2 shifts or 840 minutes, right? So that's our starting point. Now, once we have that, we will create a block layout or what we call a conceptual line design before we jump in and start doing CAD detailed drawings, because we want to test this and include the impact of variability. So that's where simulation modeling comes in. And the tool we're using is called the Lean Design Simulator. That's a simulation software that we developed or had someone develop for us. And it's included in the Lean Design Studio. And it's a discrete event simulation tool, but it's really geared towards value stream optimization or value stream modeling. And the input, the model creation, is all done in Excel. So we have a series of tabs here. We have the flow descriptions, including feeder lines. We have the list of products, including any subassemblies. We have the resources down to the workstation level and the operator level, with various parameters. We have the various flows defined. So what connects to what do I do first? What do I do second? And we have 3, they're color-coded here, 3 different flows, handlebars, wheels, and then final assembly test pack, right? Then we have a tab for process times. So for every product or subassembly and every station, so now we're down to line balancing or down to the station level, we need to know what the work times are. So this is really the toughest worksheet, I think, or the most detailed. And then we have our sequence or our dispatch list or production plan, where we list out what we're going to model and in what order. So in this case, starting with row 2 in this spreadsheet, we have the product and we have how many. And we also define if there are any subassemblies that are required, we document those here as well. So these are all the primary products, so the deliverables, and these are the subassemblies here. And we can have more than 1 or 2 subassemblies. Just keep adding columns. So we're going to build 10 of these, and then 1 of these, and then 1 of these, and 16 of these, et cetera. That's the order in which we're going to run these models down the line. Okay, so that is it. So we're going to use this model. We're going to run it, and let's try this out right now. So I'm going to go to our Lean Design Simulator. We're going to run this model and just give you a taste of how this actually works. So here we are in the Lean Design Studio. We have various courses and tools, and we have a section here called Simulation. So this is where we host our simulation modeling tool. So I'm coming over here to the Lean Design Simulator, and you'll notice there's an announcement here, Simulation Modeling Challenge. I'm going to tell you about that at the end of this webinar, so stick around. But what we're going to do here is just launch the engine. So the calculation part of the simulation tool is basically a black box. There are a few parameters you need to enter, but basically it will do its thing, and then return to us the results. So we're going to choose the input file, choose another file. So on the desktop, and here it is, Saleen Bicycle Factory Simulation. So we're going to open it up, and Bicycle Factory Simulation, we're running off a copy here, that's fine. And all you need to do is click on Simulate, and it's going to prompt us for two variables. By the way, the speed at which you see it running is real time. I'm not speeding up the video. So warm-up time is we don't want to start with an empty line before we start collecting data. So we're going to allow it to run for a certain amount of time before we start actually collecting simulation results. So we're going to let it warm up for 60 minutes, and then we're going to run 2 shifts, right? And we're going to click use variable times. Click that on. Right. So that's it. That's how long it takes. Right. So it's done. And we have a little bit of information here. We completed 661 units. Now our design goal was 719. So it looks like we have some more work to do. And then we have the results file. I'll just click on it. It's a second Excel file. And it gives us 3 tabs here. Make this a little bit bigger. So the first tab is a summary tab, summary results, and it's going to show us how long we ran. So 839, that sounds right. And we warmed up for 60, gives us the source data file, the date, the time, etc. And then it shows us the demand. That was the sequencing file we had. So here's how many we planned, and here's how many we completed during that time, right? So that's good summary results, but not terribly useful. Can't do a whole lot with that. But the main, well, I'll give you a quick view of this. Order stats is going to give you the progress of every single subassembly and every single final unit, when it was started and when it was completed through the whole process. So there's some interesting things that can be done with this, but the most useful output is this resource stats. I'll make it a little bit bigger. So resource stats is going to give us by station and also by person, by operator, a couple different things. How many entries, so how many arrivals to that station, and then what percent of that station was busy. That's kind of the value added percentage of time, and waiting and blocked and traveling and idle. And so what we want to do here is use this to look at where the potential bottlenecks would be. And we're looking for high percentages of waiting or blocked, or high utilization. Like 94% might be a flag that this station here, the final assembly 2 station, is a potential constraint. So there are some guidelines in our user manual for using the simulator for a structured analysis approach for how you would go about analyzing and identifying the bottlenecks. Also, we want to look at the labor part of it and look for, again, the same kind of thing. Do we have some labor resources that are way underutilized or overutilized? In this case, our final assembly operators are running at about 75, 76, 77%, and that's probably lower than we'd like. That's a fourth of their time is non-value adding. So we can do things here to adjust our staffing of this, as long as we maintain our throughput. Okay, and then the utilization on some of these feeder lines seems to be better, right? Close to 90%. Okay, so we identify based on this output where the opportunities to improve, because remember, we're not achieving, at least in this example, what we want to achieve in terms of throughput. And then we go back to the model and make adjustments. So if I go back to Excel, I'll just point out to you, sorry, I was in Excel, wasn't I? Go back to the model, I'll point out to you the control points. So the control points are basically under resources. We can control the number of operators. So I can add people and take people away simply by changing these numbers here. So instead of 10 operators in final assembly, let's see what happens when we run it with 9. Now, that assumes that these operators can flex. So that's kind of a baseline assumption that they can work at more than one station. But if that is possible, then let's see what kind of results we get. The other control point, I notice here that we have no buffers. So that was something you would have done at the design stage, but certainly that's going to help throughput quite a bit if we add some buffering here. And then the variability here is set to high. That may not be the case. If people are well-trained and reasonably consistent, maybe using a high variability of the labor time is overkill in terms of variability. The other adjustment piece, which is just as important, if not more so, is the sequence. So this is the sequence we use to test it, but we can define any number of different sequences. That's the order of production. And if we know that there are some high work content products that may be constraining the output, we can do something about that. So we can define in a high level of detail, actually, the sequence of the work flowing down the line. And that's typically something that we would do based on sequencing rules that we would have developed earlier, and we can continue to refine over time. But we apply the sequencing rules to our backlog. Here's what we need to build based on customer orders, and then we would put it in the right order to optimize the flow. So basically, adjusting staffing and adjusting the sequence are things that we would do more or less on a daily basis, just to validate the plan. And if we have a good planning system, scheduling tool, and we've done a good job of line design, then the need to make a lot of adjustments every day may be small. But on the other hand, if we have a wider variability of work content in the products going down the line, then we need to be more diligent in terms of validating our production plan and fine-tuning it, because our scheduling or planning system may not be able to do this level of analysis. It may be a great tool, but it may not have the ability to do discrete event kind of analysis. If it does, that's great, and maybe you don't need this at all. But chances are good that it probably doesn't do that. Okay, so that's it. So we would make changes to our model. We would reload the model, right, with the new data file. Could be the same file name, but we made changes, and then we would rerun it until we get to the point where we are going to be happy with the results. And at that point, we would release it to production, right, to manufacturing. Here's a plan that has been validated using our virtual factory, right? So we've optimized it, and off we go. And the expectation then is we should be getting better results, right? By taking this approach. Okay, so I think that's all we need. I'm going to go back to the webinar, and hopefully this was less time than before, and let's continue on.